Alright, hey, welcome back to part 3 of retro computing. I want to move into assembly language now. We want to keep in mind the machine language coding of things as we move forward, but we want to generally work in assembly language. And the easiest way to start messing with that is just to use the front panel simulator. It's got a built-in assembler, disassembler that we can play with. So let me set our stack pointer. So I'll deposit 1,000 into the stack pointer, and if I examine the stack pointer, it's 1,000. That's because if anything happens that tries to use the stack and the stack has a value below 400 hex, we get a type of trap, and it puts the CPU into a different condition. So we want to give the stack pointer some reasonable value, like 1,000. And I'm going to do some coding around location 400. So I'll put a 400 in the PC, and I can start writing instructions by saying, for example, deposit 400, clear R0, deposit 402, increment R0, deposit 404, branch to 404. And now if I say examine 0 to 410, I can see, examine 400 to 410, I can see the binary pattern stored in those locations. If I say examine -m 400 through 410, it will disassemble those instructions. So I can see at 400 it says clear R0, and then increment R0, and then branch to 404. So my program counter is set to 400. I can now start stepping. I'm going to clear R0, so R0 is a 0. If I step again and I examine R0, it's been incremented. And you can see I'm sitting with a PC of 404, and if I keep stepping at this point, it's just going to keep branching back to that location. So that's a real super simple program. Let's do something else. Deposit 400, move immediate 12 into R0. Deposit 404, move immediate 3 into R1. And then deposit 410, add R0, R1. And if I examine those locations, I can see, first I'm moving a 12 into R0, and then a 3 into R1, and then I'm going to add them. Now if I examine these as just words, you can see here's the opcode and addressing modes for move into R0, but it's using addressing mode 2 with register 7. That's our immediate addressing mode we talked about in the last video, and it's followed by the actual immediate value 12. Here's a move into R1 followed by the immediate value of 3. So let's put the PC back to 400. R0 is still a 1, R1 is a 0. Let's go ahead and step. So this says first, I moved a 12 into R0, and there's the value. And now if I step, I've moved a 3 into R1, and now if I step once more, I should add 12 and 3 and put the result in R1, and there's our 15. So pretty easy to sort of play around with. If you have a command or an addressing mode, you're curious what exactly it does, we can mess with it like this. And so that's a useful way to sort of play around with some of these instructions, get more familiar with them, and so on. But it's not really what we want for writing more complex programs. So we're going to want to use something more powerful, and that's a cross assembler. So I'll put a link to this Git repository in the description, and it's got a number of good resources in here. In particular, if we go down to cross assemblers, we can look at Macro 11. That was the assembler for the PDP 11, but it's also got assemblers for other architectures as well. Cross assembler just means it runs on one system but assembles code for a different system. So this is running on, for me, an x86 based Linux machine, but it's assembling code for a PDP 11. And this works pretty well if you just download it and do a make. It builds it up nicely. It's got the source code. It's all just written in C. It's got a good README. And once you make this tool, you get an executable called macro 11. And that will take an assembly language program and convert it into an object file. And then there's a Perl script called object to bin that will take an object file and create an output file. And we can specify a particular type of output file that the PDP-11 simulator can ingest very easily. It's basically a paper tape format. And so we can start to piece together a tool chain using these tools, which are super convenient. So let me open up a window here, and we'll come back to our simulator in a little bit. Here's a simple macro program. I'm going to start at location 100. I'm going to put a 400 into my stack pointer. I'm not going to actually use the stack. I'm going to move the contents of 177570 into R1. That is the register that corresponds to the switches and the LEDs. So I'm going to read the values on the switches. I'm going to increment that value, add 1 to it, and then move it back to that same address, which will display it on the switches on the front panel. So if I have my front panel set to 0, I should get a 1 coming out. If I set it to 4, I should get a 5, and so on. Pretty simple test. Alright, so I've got this program, right, and you can download from BitSavers documentation on the macro assembler, but it's fairly straightforward. Asect, as far as I think about it, just says I want to specify absolute addresses. So I'm putting my code at location 100. You can have labels. When I say end start, that says it's going to initialize the PC to the address of this label, which is going to be location 100. Alright, so let's assemble this. So I've already built that macro 11 and put it in my path, and if I just say macro 11, I'll get a usage information. Basically I can specify an output file, a listing file, input file, and then other various options. So here's the way I'm going to do this, and I've got a nice bundled up tool chain for doing all of these steps we're about to do, but let's go through it and just see the long version. So I'm going to make an output file called test.object. I'm going to make a list file called test.list, and what I'm going to compile is test.mac. So those suffixes are not critical, but they're kind of conventional. So I'm going to do that, and if I had a mistake, I would get an error message. Sometimes a horrifying error message, like about memory allocation errors and stuff. But no messages. That's good to go. And if I do an ls, I can see I had my Mac file and it created an object in a list. So if I look at that test.list, this is the best file, right? This shows me my original code over here on the right, but also what the assembler translated it into. So this is an address, location 100. It stored this instruction followed by this instruction. Well, that's that move immediate instruction, right? 400 was right here, and we moved from register mode 2 on the PC to register direct register 6, which is a stack pointer. And then we moved from this location 177570 into register 1. This used a different addressing mode, 6. It made it relative to the program counter instead of storing an absolute address. So this code is more relocatable. But anyway, that moves the contents of this location into R1. And then this is an increment on register R1. And then we move register R1 into, and this relative location still corresponds to 177570. It's a different relative location from this because the program counter has a different value here, right? And then we do a branch to start. So what does branch look like? Well, 770 777 would be -1. 776 would be -2, and so on. So if you look at this value, multiply by 2, add it to the PC after this instruction is fetched, which is 120, it'll branch you back to location 100. And then there's, symbol table, collects all your symbols and tells you what the values were, and so on and so forth. So that's the listing file, and when you're debugging your code, you often want to go back and refer to that. Alright, so the object file is not terribly human readable. It looks like this. And we can see, some of the values from our object file are stored directly in here. So these displacements, for example, 17460, 17452, there's the 460, there's the 452, right? So this file contains a version of the words corresponding to our assembled program, but with some other information in there as well, such as what address these should get stored at in memory. So the other thing we're going to do is we're going to use this object to bin, which is that Perl script, and I'm going to say, let's use binary format, and my output's going to be test.tape, and the program I want to convert is test.object. And I made a typo. Let's see, binary output equals test.tape. Does not like the output option. Oh, it's a file. Alright, so now if I look, I've got a new file at the bottom which is called test.tape. And if I look at the contents of that, that's a pretty simple format. It's basically a header, 0 and 1, a byte count, a starting address, and then that many bytes followed by a checksum. And then if there's another block, it would have byte count, starting address, the actual bytes, and then a checksum, and so on and so forth. This is a well understood format, and in particular, the simulator will actually ingest those files. So if I check my directory, oh, I'm not in the right place. Let me just change directories. Alright, so now I'm in the same directory as I am over here. So I can say load test.tape, and it will pull in that file. The macro file, right? So if I examine my program counter, it's set to 100, and if I disassemble, I can see that this is the program I just wrote. Move 400 into the stack pointer, move this number into R1, increment R1, move R1 back into 177570, and branch back to 100. So I can step through this, and I can see it looping. I can step through it from the front panel, or I can enable free running, and I can just tell the processor to free run, and now it's executing my loop. So if I flip this knob over to display register, it will show me the contents of that display register I've written to. Well, my switch is all zeros, my output is 1. If I set my switches to 1, my output is 2. If I set my switches to 3, my output is 4. If I set my switches to all 1s, my output goes to 0, so it overflows. So again, pretty simple test, but it's a nice way to sort of get our hands dirty with playing around with some basic assembly language code. So let me show you how I set up a tool chain for this. And it's nothing magic, it's just some basic bash scripting. So I can just say Mac and put in the name of my file. It makes sure I specified a file name, that's the root name, make sure it exists, and then calls macro11, creates an object, which is my root name.object, creates a listing file, assembles the macro file, puts all the output, including any error messages, into cat and captures that output. If there was no output generated, then everything is fine. If there was any output, I'll echo it and say something went wrong and exit the script. So it picks up errors. Otherwise, I'll go ahead and say making into a tape. I'll call object to bin, and again specify the output file, the source file, check for errors. And if that all succeeds, I'll just say, you know, created the output file.tape, and we're done. So I'm in my my work area. I can just say Mac test, and we're good to go. There's the new test.tape. So if I change test.mac and let's say let's add 2 to our register and display it. So I can say Mac test, and then if I just go ahead, let's halt this so I can do a Control-E to get back to the simulation. I can say load test.mac, test.tape, and then say continue, and now it should be adding 2 to whatever value I specify. So if I put 0 on my switches, I've got 2 coming out. If I put 2 in, I've got 4. If I put 7 in, I've got 9, and so on and so forth. So very rapid prototyping at this point. Let's decrement R1. Load it in, run it, and now whatever value I put on the front panel switches is being decremented. So if I put in a 1, I get 0. If I put in 0, I get all 1s out, and so on. Put in a 4, there's a 3. So this is what we always want, right? When we're working on a computer, we don't want to be slowed down by our tools. We don't want to be doing things other than what we're interested in doing. In this case, we want to write assembly language code, get it into the system, see what it does. So, you know, my whole process is just a single command, just Mac and the name of my file, and then over here I can just say load. Also, my simulator that I run, PDP, is a wrapper around the simulation code, but I also use RL wrap, which is a great little tool that lets you do command line recall. So every command that I've typed, within reason, I can get back to, and I can go forward and backward and so on. And that's handy, right? I know that every time I test this, I'm going to want to load it and then continue, and then I might make some changes and then load again and continue, and so on. Just things that, you know, make your life a little easier. So that's some basic assembly language, and using the macro11 assembler, and then using object to bin to convert it into a binary file that we can load in using the load command. So that gives us a quick way to build code, pull it into the memory of the simulator PDP, and then test it. So that's all I got for this video, and we'll dig deeper into some specific programming in the next video in part 4.